Power. Power is the rate at which work is being done on an object. Power is how fast you're doing work. Anytime we talk about a rate, it means you're dividing by time. Power, symbol capital T, capital P, is work divided by time. There's your punchline. Power is work divided by time. So let's look at walking up the stairs back behind my room over here. If you walk it slowly or if you walk it quickly, you'll do the same amount of work because the work done going upstairs is mgh. Is it more tiring to walk up the stairs or sprint up the stairs? What's more tiring? Yeah, why? Because you're generating more power because you made time smaller. So if you're exercising, you're getting tired. It's not because you're doing work, it's because you're generating lots of power causes tiredness. It's the difference between going for a walk and going for a run. It's the difference between walking upstairs and sprinting upstairs. The faster you do work, the more power you need, the more tired you'll be. What would the units for power be? Well, who remembers what are the units for work? I know it's from before spring break, but joules. What are the units for time? So power is measured in joules per second. However, the concept of power is so important that we give a joule per second a special name. Power is measured in watt? Watts. Symbol capital W. And this is where it gets awkward because there's a capital W in the equation, that's work. And then in your answer, there will be a W after the number, that's units. I've mentioned that probably once or twice before that we've run out of letters in our English alphabet. Sorry. Power is also a scalar. So, let's suppose, for example, you're a crane operator, and let's suppose you've been given the job to move a safe up to a height of 12 meters, about roughly 4 stories. And you're going to lift it up with a crane and move it through the window. You can't get it up the stairs because the safe is too big to fit in the stairwell. If you want to do the job in 11 seconds, how big a motor do you need? What's the power output of the motor? So an electric motor is used with a pulley and rope to lift a 6,650 Newton load from the road to a height of 12 meters. The job is done in a time of 11 seconds. What's the power output of the motor? What's this question asking me to find? What is the? So let's write down our new equation. Power is work over time. Can everybody underline the word lift, please? And then you can draw a little arrow pointing to it. We said this, the work when you're lifting something, and if you want to, you could add this to your purple formula sheet. It's mgh, because we said when you're lifting up, the force that you're resisting in your free body diagram sky is equal to mg, and the height is h. So, on the top of my equation, I'll have mgh over t. What's that 650? What? Good, yeah. It's not the mass, because it's newtons. It's mg, so I can actually replace mg with 650. What's the height, Petco? What's the time? What do you get? You get 709? 709. Power is measured in watt? Watts. If you need the job done in less than 11 seconds, you cannot. You need a bigger motor. A motor that is capable of putting out more power. You can do it slower, just don't run the motor at full speed, full throttle. So this is kind of a whatever, but you could also solve for time. How would I get the T by itself in this power equation? Okay? And you can use that if you see the big cranes that build skyscrapers, you can make a fairly accurate representation of how long it's going to take you to get all the material up by doing how much mass of material we need to build the skyscraper, what the power output of our crane is. Okay, we need to have this crane for X number of days because we can't possibly get the material to the right heights in less time than that. It's a pretty trivial calculation. Watts are the official metric unit of power, the SI unit. But another unit, the imperial unit of power, is the horsepower. Horsepower is a stupid unit. It was invented by James Watt. James Watt has a unit, the watt, named after him. To me, I think he's one of the most overrated science people around. He really, in my opinion, didn't contribute much to physics. But he was a good promoter. People will often say he invented the steam engine. No, he improved the steam engine. And then he went around to farmers because he wanted to sell steam engines to farmers. And a farmer would say, what good is this? And so James Watt made up a unit, the horsepower. So if he said to a farmer, this engine is 3 horsepower, what does the farmer think? This engine can do the same amount of work as 3 horses. Nonsense. James Watt did not do any calculations to that effect. Nothing. It was purely a good shtick. So good that we still use it. Car motors are still measured in horsepower. Who the heck now knows how much work a horse can do? You haven't grown up around horses all your lives. Anyways, there's my rant. 1 horsepower is about 750 watts. So this motor would have a horsepower of, I want to convert this to horsepower. How will I do that? Write down what they gave me. I want watts to cancel, so where will it go in my next fraction? On the, I guess horsepower is going to go on the top. And here's my conversion factor. 1 horsepower is 750 watts. So what will I do with that 750 since it's on the bottom? Will I times by 750 or divide by 750? Answer button, divided by 750. This is a 0.945 horsepower motor. If you were to sprint that set of stairs as fast as you can, I've run the numbers. If it took you about 1.5 seconds to get up those stairs, you're almost bang on 1 horsepower. Most of you are capable of putting out 1 horsepower, but for short bursts. If I said sprint 50 flights of stairs in a row, none of you could do that. Okay? But almost every one of you could sprint 1 flight of stairs really, really quickly. Oh, here we go. A 60-kilogram girl runs up a flight of 3.32 meter high stairs in 2.6 seconds. What's her power output in watts? So this wants me to find power, which is work over time. The time is definitely 2.6 seconds. When you're going up a flight of stairs, what's the work done against gravity? So you might have written work lift is mgh. If you really want to be more general, work against gravity is mgh. Force times distance, h. You see it hidden? Force times distance hidden inside there, Harsh? See it? Force times distance. mg, get the obvious one for it, okay? So this is going to be mgh over 2.6. What's the mass of this girl? 60. G, 9.8. H, 3.32. All over 2.6. What do you get? Units, power is measured in watt. And so if 1 horsepower equals 750 watts, what's her power output in horsepower? Almost exactly 1 horsepower. The stairs here, back here, are right around 3.3 meters high. So if you ran those in about 2.5 seconds, fast, but not crazy fast, you're putting out about 1 horsepower if your mass is around 60, and most of you have a mass-ish around 60-ish, give or take. So the horsepower was invented by or defined by James Watt, who was looking for a way to describe the power of his newly invented, improved steam engines in terms that people accustomed to using horses to do their work could understand. Example 3. Sam, what's example 3 want me to find? What's example 3 asking me to find? Yep. Time. I don't see a VI, a VF, and you know what? We learned a new equation today that has time in it. Power is work over time. Sam, do you get the T by itself? Where is the T right now in the original equation? On the... Ugh. Oh, wait a minute. Stuff moves diagonally. I can multiply the T to there, yes? And now I just need to move power to the other side. How would I move power to the other side? So here is yet another equation. I don't know how many equations for time that we have. Time is also work divided by power. So this is what you would use, say, a good example would be if you're using those big cranes to unload cargo ships in the Port of Vancouver, you would know how much mass you had to move, how high you had to lift everything, and you would have a pretty good indication of just how much physical time it's going to take you to unload and lift that much mass off of a ship. Can you all underline the word lift? How do we figure out the work done when you're lifting something? What's the equation? What? MGH over power. Looks like the mass is 500. G, 9.8. H, 30. All over power. Ooh. Can I put 10 into this equation? I'll have to do a conversion. So over here, I'll make a little note. 10 horsepower. I want horsepower to cancel. So where is it going to go in my next fraction? On the... I want watts to be my unit left behind. And the conversion factor was 1 horsepower is 750 watts. Kyle, can you go 750 times 10 in your head without a calculator? Thank you. How much time will it take this motor to lift this safe up the window? 30 meters. Up to the 30 meters. 30 meters, about 10 stories. How much time will it take? Let's find out. Oh, you get 19.6 seconds? If you need it done faster, you need a bigger motor. Power is also sometimes measured in kilowatts or megawatts because 1 watt is not very big. So you'll often hear them talk about how a dam can put out megawatts of power or kilowatts of power. And now you understand that a bit more in context. When they say a dam is capable of putting out 5 megawatts of power, that's saying it can put out enough energy to do 5 million joules of work per second. Example 4. Couple more examples. Yep, we're good. The power of a light bulb is related to the amount of electrical work or electrical energy it consumes in 1 second. So a 40-watt bulb uses 40 joules of electrical energy in 1 second. Where's the work done there? There, the force times distance is moving electrons around. And in a normal year, we would get to that, and we would actually show you how you calculate that. And I'm not going to get to electricity this year, sadly, but it's really neat. Okay. So what's the power rating of a bulb that contains 4,200 joules of energy in 70 seconds? Other Matt, what's this question asking me to find? I know I've been talking, it's first day back. Sorry? Power. So power is work over time. Did they give me a time in this question, Matt? No. Keep reading. Did they tell me how much work is done? How much energy, electrical energy we used? 4,200 joules of electric energy. Okay. How many watts is this bulb? You might even be able to do this one in your head, because I think it ends up being 420 divided by 7. 60? Even, yes? It's a 60-watt bulb. Okay. A microwave is rated at 1.2 kilowatts of power. It's running for 6 minutes. How many joules of energy does it use? What's this question asking me to find? Work. Okay. Power is work over time. How would I get work by itself? How would I get the W by itself? How do I move the T over? Yep. Work is going to be power times time, or time times power. How much power? 1.2 kilo. Kilo is 10 to the what? It's on your formula sheet if you forget, but 3. So there's how much power, 1,200 watts. Time, ooh, why can't I use the 6? Minutes, how would I convert minutes to seconds? So I'll just do this on the fly, 6 times 60. How many joules of energy will the microwave use? How many joules of work did the hydroelectric dam need to do on these electrons? You only get 432,000 joules. So you run a microwave for 6 minutes, it's almost 500,000 joules of energy used up. It's almost 500,000 joules of work that the hydroelectric dam had to do. What I'm really saying is, Percy, a joule is not very big. In fact, if your parents received their energy bills, your parents are charged by BC Hydro how much energy they use. If they received their bills in joules, they would freak, because most houses use a few billion joules of energy a month, and people don't have a good grasp of numbers that big. Many people that don't have a strong math background don't know the difference between a million and a billion and a trillion. They don't grasp that concept. And so another way to measure energy that most electric, in fact, all electric companies use is a kilowatt hour. Now, kilowatts, what's that a measure of? What do I have? Power is measured in watt? This is power. What's hours a measure of? Time. So a kilowatt hour is work. Not our standard metric unit for work, but it is another way to measure work. 1 kilowatt hour is 3.6 times 10 to the 6th joules. So how many kilowatt hours does this question use? How many kilowatt hours of energy does this microwave use? They want me to convert 432,000 joules of microwave energy to kilowatt hours energy. I guess I'll write down what they gave me. Marcella, I want joules to cancel. Where's it going to go in my next fraction? On the... Yep. And I guess I'll put kilowatt hours on top. And again, here's my conversion factor. So I guess a 1 is going to go right there. And a 3.6 times 10 to the 6th is going to go right there. Am I going to times by 3.6 times 10 to the 6th or divide? How do I know? It's on the bottom. This is that unit analysis, dimensional analysis trick I showed you last year. Those of you that are in chem, I'm willing to bet you're using that fairly often to do a lot of your conversions. It's a handy thing to have in your pocket. So it's going to be this divided by bracket 3.6 times 10 to the 6th. 0.12 kilowatt hours. So all electric companies, they bill people not by joules, but by kilowatt hours. And that way, a standard house uses about 1,000 kilowatt hours a month, which is, most people can still understand 1,000 and they can grasp that concept. But if they had several billion kilowatt hours, they just wouldn't be able to interpret it. So kilowatt hours, even though it has the word watt in it, it's a measure of work energy, not power. Oh yeah, I have a photo, bad physics. I think I have a photo bad. Oh, it's physics 11, Mr. Dewitt, because you're using the old physics 11 unit notes. Here it is. This was on a bus stop here in BC. I saw it in downtown Vancouver. It said, burn calories, not kilowatts. Burn energy, not energy. That's wrong. Bad physics.
My apologies for the interruption, staff. I just wanted to give you a heads up, an update, I should say.
Example 6. A hot dog takes 40,000 joules of energy to cook. If a microwave is rated at 800 watts, how long will it take to cook a hot dog? Grace, what's this question asking me to find? Time. What's that 40,000 joules? Work. What's that 800? Got to be power, because power is measured in watt. Is there an equation that has time, work, and power in it? The brand new one. Can you get the T by itself, please? Yeah. So it's going to be 40,000 divided by 800. And this is how they calculate if you're nuking some food and you're following the instructions on your microwave and it tells you how long to turn your microwave on for. This is how they calculate how long you need to have your microwave on for. So 40,000 divided by 800, 50 seconds. Okay. Little note though, Typically, microwaves come in two main styles. Small microwaves are usually 800 watts. Large microwaves are usually 1200 watts. So if you're using a larger microwave of 1200 watts, how long would this microwave take to cook the hot dog? Well, now it would be T equals 40,000 divided by 1,200. And 33.3 seconds. And this is why if you ever look on the back of a microwave package that you're microwaving, it always says microwave oven times may, you've seen the phrase. What does it say? Vary, yeah. Because they don't know whether you're using an 800 watt microwave or a 1200 watt microwave. Hashtag nerd trivia. Turn the page. Power is work over time, but there is a special version of the power equation if you are moving at a constant speed. So you ready? Underneath the box, but not in the box, can you write power equals work over time? Work is equal to what times what? Force times distance over time. And then do me a favor, can you circle the D and the T, please? What do I measure distance in? Meters. What do I measure time in? What is meters per second? Speed, because we're in you said velocity, we're in scalarville here. So speed, another way to measure power, a special version, if you're moving at a constant speed, if you're not accelerating, so the force is constant. Force, the net force on you is 0, the forces are balanced, times speed. Mr. Dewick, how can you have a force but not be accelerating? It just means there's another force in the opposite direction. You know what? Let me give you a good example. If you've ever ridden your bike as fast as you can, eventually you can't speed up. And that's because the force that your bike is applying to push you forwards is exactly being canceled out by air resistance. Okay? So how much power are you generating if you need a constant force of 32 newtons to overcome air resistance while pedaling your bike at 12 meters per second? So what's this question asking me to find, Mansion? How much what? 7A? How much what? Say it loud and proud, you're right. So don't write this down. Don't write this down. My first thought would be to go, well, work over time. Mansion, do you see a time in this question anywhere? Do you see a force?
Oh, sorry.
Yeah. First of all, do you see a time? No. Do you see a force? Now I might say this might be a case for my special subcase version of power, force times speed. Did they give me a force? Yes. Did they give me a speed? Okay, so this is the checklist when I'm asked how much power. I first think work over time, Armand, but not always. In this case, it's going to be 32 times 12. $384. Power is measured in watt? Watts. Okay. If you want to go faster, this is meant to be obvious, will you require more power or less power?
More power.
If you want to pedal faster, will you get more tired or less tired? Yes, power is tiredness. Not work, power is. Okay. Or you can scrunch down in a more aerodynamic position and reduce the force of air resistance, which gives you a slightly more unbalanced force forwards, and you can increase your speed a little bit. The other way of doing it. And now we're starting, if any of you cycle competitively, now we're starting to explain some of the physics behind competitive cycling. Okay? There's a reason why, Jack, they all assume the same position in the Tour de France when they're, coasting, right? What's your homework? Number 1 is good. I'll skip 2. 4 is good. 3? Can't you see number 3? I see number 3. Is there something wrong with you? You all see number 3, don't you, people? Harsh. You better be a little worried because all of us see it at number 3. Okay. 6 is good. 7 is good. 8 is good. 9 is good. And 10 is good. 10B we'll learn next lesson. So you can also work on your forces materials, okay? And I think I said to you, you've noticed we're doing a little bit of forces and stuff here too. There's some overlap between forces and work and energy.